How to force a momentum change in the perfect bounce basketball shot.
Hey, Mr. Levesque. So what we did for our project was the perfect basketball shot. So what that entails is standing, it ended up being 14 point some odd number meters away from the basketball hoop, and I threw the ball and bounced it. So here is that video. Okay. So for constants in this experiment, the mass of the basketball was 0.62 kilograms. The distance from the initial starting point, so right there, to the hoop came out to be 14.2361 meters. The hoop itself stood 3.429 meters, and that's it.
So for the free body diagrams, when it's at rest in Andrew's hand, an object at rest has to stay at rest, so the force of gravity is cancelled exactly by the normal force, and it stays where it is without any sort of force acting on it. And then when it's at the bottom, the force of gravity is constant and thus is still there, as it always is, but the force that it was thrown with is still there and is pushing itself against the ground before it's going to rebound up into a higher position. And at the top of its orbit, or at its parabola, the force of gravity is obviously still there, but this force in the x direction is prevalent because the force of y is negated basically by the drag force, and it reaches higher than its initial height because a force was acting on it, so the laws of conservation of energy don't actually apply because of the force that was acting on it initially. And then finally, the force about to go in, the same force is acting on it, and the force of gravity is continually acting on it as well. So using Video Point, we took 73 frames of motion, and using that same software to track the time, which was 2.3866 seconds, displacement in the x direction, displacement in the y direction, y acceleration, y velocity, x acceleration, and x velocity all through those 73 frames. So in answering our essential question, a couple equations that we used to analyze this type of motion was work equals force times the x component of the displacement, which is the displacement in which the work is being done. Power equals that same work divided by time. And then we move on. Momentum equals mass times velocity. And the vector quantity of that momentum is just the square root, the Pythagorean sum of those x and y components. Force equals the derivative of momentum with respect to time. And then along those same lines, impulse, which is the change in momentum, equals force times change in time. The total energy equals the kinetic energy plus the potential energy. That kinetic energy equals half mv squared, and potential energy equals mgh. How to force a momentum change in the perfect bounce basketball shot.
So using that data from Video Point, we decided to make data tables of certain aspects of the bounce. So the first one we did was using the equation previously explained. For momentum, we found momentum in the y direction, the momentum in the x direction, and then using the Pythagorean theorem, we did the momentum vector. We also used the potential energy equation and found this entire set of data for the basketball. We also used the kinetic energy equation for this entire row of data points, and then we added these two rows of data using this equation to find the total energy. From there, we also found, using the work equation, we used the x values from over there and the force to find this entire column for work. We used the power equation to take that previous work column and divided it by the time to get the power row. For impulse, we used a force times the time column, and for force, we used the change of momentum over change in time.
So using that data to answer our essential question about force and momentum, we graphed momentum versus time, and there are 3 stages to this for our whole graph for the whole around 3 seconds. So we broke it up into 3 stages to analyze each individual one more completely. So for the first 0.12 seconds in this graph, momentum versus time, we found that the slope of that, or the force required, was around 10.952 newtons. So for the second increment, the force for 0.3866 to 0.7866 seconds was 35.603 newtons required to do that amount of work. And for the final 0.82 to 2.3866, it took about 4.366 joules of work to complete that. So we also analyzed power as work over time and had some similar these various stages. So we analyzed each one individually. For the first 0.5533 seconds, we found that power for that increment was 706.58 watt, and then for the second increment, it required about 8,180 watts to complete that work. And for the final one, it took about 2.22 watts, according to our data.
The error in this lab was external factors, such as air resistance and wind, also instrument resolution of video point, and the accuracy of a mouse click. The purpose of the lab was to find the force and momentum required for the perfect basketball shot. Our experiment was filming the basketball shot and using video point to analyze the data.
For the first 0.12 seconds, the force required was about 10.952 newtons. For the second increment, it was about 4.366 newtons, according to our data. And the final increment was about 35.603 newtons, and that was calculated using momentum versus time.
Overall, we were successful because we found what we were looking for.